Okay, I want to show you how to do curve fitting within Excel now. So what we have here is we have some data of free fall of an object. And you can see kind of the governing equations right here for the velocity and position of this data. Okay, so basically you're measuring the velocity and position of, an object falling every quarter of a second. Okay, and you don't need to understand where these equations come from, but just know that the velocity is determined as the acceleration due to gravity times the time, and the position can be found by 1/2 that time or that acceleration due to gravity times time squared. And the acceleration due to gravity is 9.8 meters per second squared. Again, that's a common thing you'll learn in physics if you don't know that already. So what I want to do is I'm going to start with that velocity data. Okay, and I'm going to select this data. I'm going to go ahead and create a plot. Okay, and we've done this before. We want to do a scatter plot, and we just put the dots in there like so, and there you have it. Okay, and again, you go through, you can create your labels and everything, but we've got the velocity on what we call the vertical or the y-axis, and then time on the horizontal or the x-axis, which is exactly what we want. Now, for this, what I want to do is I want to go ahead and fit a curve. And we know this is a linear curve. You look at it, you can see that it's a linear curve. So let's go ahead and fit that. So I'm going to right click on the data and go to add trend line. Okay. And when I go to add trend line, you see I have these different values here. This is a linear one. We're going to stick with that. Okay. There's all these other ones. We'll talk about those when we go to talk about the position value. Okay. Now, two things that are pretty important to include on there. The whole reason of fitting a curve is so that we can get an equation in engineering. So you want to display the equation so you see exactly what the equation is. And then you want to display the r squared value. Now, we won't go into great depths about how to calculate the r squared value, but just know the closer that is to 1, the better the data is. And we're really looking for like 0.95, 0.99, pretty high numbers that we're looking on this r squared value. And you see for us here, this is a pretty good fit. 0.9987 is a very good fit, okay? And you can see that our equation is 9.8786x, okay? And what that is, plus 0.0254, okay? And remember what that is it's representing this velocity as a function of time data, where velocity is my y value, remember, and time is my x value. And you can see this is a pretty close equation to what we should be getting, which is 9.8t, a little bit off on that. Now, there's some different things that I can look at with this trend line. One thing is I can force the intercept, say, to be 0, right? Um, when that's unclicked, it just fits the best line it can possible. If I know that that y-intercept needs to be 0, I could force that. And you can see that I still have a pretty good r squared value. And you can see that my 9.8 is still there. So you can do that if you want to. Okay. A lot of times, whatever is given is fine. It just depends on the type of data that you've got here. The other thing that's kind of helpful here is the forecast. Okay. I could forecast forward to increase the line, kind of see what looks like moving forward. So if I go one period, and period is basically one value. So again, we stopped at 2, it's going up to 3. It doesn't really know, what those units are. We do. Move forward 1. You can see it just extends that line out. You can see what's going on. You can go backwards as well. Although that doesn't make a whole lot of sense, but you could go backwards and forwards and kind of see how the plot looks moving forward. So again, usually 0 is fine. Leave that alone, okay? And the y-intercept, things of that nature. So that's how I can go ahead and place that linear curve on there. Okay, now let's take a look at the position data. So I'm going to make a new plot. I'm hitting the control key, going to highlight these two columns, and I'm going to go ahead and insert this scatter plot as well. Okay, and it puts it there. So let me just kind of make this so you can easily see what's going on. Okay, and you can see now that if I want to go ahead and fit my curve to it, my trend line, okay, that linear curve, hopefully you recognize it, that doesn't look super linear. Okay, I can go ahead and put my equation, my r squared value. You can see that r squared value 0.95, yeah, it's good, but it could be better. So this is where you either understand the physics behind it, what it should look like, or you can kind of experiment with things with these different types of tread line. For example, is it an exponential, okay, which is basically e to some power. You look at that and you say, well, yeah, that's a worse r squared value. Is it logarithmic? Oh, that's even worse, 0.769. Okay. Is it, I'm going to skip to power. Okay, well, now power, this one looks pretty good here. Okay. Um, I get a 0.9998 value here. Okay, so I'm feeling pretty good about this. I look at my equation and it's 0.481 x to the 2.0015, which is pretty darn close to what I have right here. So this is a power value that we're looking at on this. Okay. Now, it might be better to think about it as a polynomial. Okay. However, then I get these extra curves going on here. I still get the 4.9x squared. It just kind of, again, think about how the data should look. Maybe if I set the intercept to 0, okay, but it's a little bit off, okay, but it's definitely following the trend that it should look like. Now, what you want to be careful with is this polynomial, because what you can do, again, we've realized that x squared is a good fit. You can either think about it as a second order polynomial or a power equation. Both of them fit pretty well. Again, x to the 2.001 maybe isn't ideal, but then having this extra x and other equation maybe isn't best either, but you can see that I get a good fit. Now, watch what happens as I increase the order of the polynomial, which is basically going to take it from a squared value to a cubic value. Okay, okay, and I can keep increasing this. Okay, and you'll see that eventually I'll get to, hey, I have perfect fit. Now, this is where you want to be really careful, because with polynomial, generally you can increase the order enough that it'll fit through any curve you want. Okay, there'll be just the way math works, and I don't want to get into the math of this, but it'll fit to that curve. Okay, that does not mean that's physically what's happening, and the best way to demonstrate this is with that forecast. So let me go ahead and forecast forward a couple of periods. Okay, a couple of seconds, and look. Well, let me just do one maybe. Oops, go up to 3 seconds. You can see what happens. Okay, yes, that curve fits perfectly, but physically this makes no sense. Okay, because what this is saying is that the position falls at, to certain positions until 2 seconds, at which it turns the other direction and shoots basically in the opposite direction a huge amount, which is, we know what doesn't happen when you drop an object on Earth, right? It continues to fall in the same direction. Okay, so even though my r squared value is 1, you want to be very careful and not just blindly use equations that give you the best r squared value. You need to understand, or at least attempt to understand physically what's happening with the data, and then fit the appropriate curve to it, right? Because notice, if I go back to a second order polynomial, which is what we expect it to fit, this is more along the lines of what we expect to see. Okay, the r squared value is still extremely good. I mean, it's not perfect, meaning that it's 1. However, this follows what we expect that path to continue on with. So again, you just want to be careful with using those polynomials, especially for data that you need to, what we call, extrapolate moving outward, which is data that goes on past the data that we currently have. Okay, so that's how we fit a curve. That's how we get an equation. Um, and you just want to be careful and make sure that you're fitting the appropriate equation for the data that you have.